Okay, just a reminder that the first assignment is due at the end of next week. So if you're struggling with that or haven't made much progress, please get on to it. And if you need any assistance, please have a look at the schedule for the labs and show up to a lab and ask a tutor there for some assistance. So today we're going to talk about games, which is Module 5, and it corresponds to Chapter 5 in the textbook. And if we have some time left over, we may pick up on a couple of leftover topics from earlier modules, so reactive agents and possibly motion planning. So we'll just see how we go with this. So talk about the origins, motivation, minimax search, heuristic evaluation, alpha-beta pruning, and then we'll have a look at some specific types of games, stochastic games, partially observable games, and continuous embodied games. And as usual, I encourage you to go have a look at the videos on the Open Learning website, which have some more details. I'm going to kind of give more of a summary. Some of the details may be missing. So the origins of this. So Wolf, it may interest some of you to know that the very first chess-playing machine was exhibited back in 1769. It was called the Mechanical Turk, which of course has become a website for crowdsourcing. It was designed by Wolfgang von Kempelen, who was the chief engineer in the court of Maria Theresa in Austria, who's best known to us as the mother of Marie Antoinette. Basically, a magician came to the court and gave a display, and von Kempelen was very unimpressed and said that if he had a few months to prepare, he could put on a much better show. And so he banged away in his workshop for 3 months, and this is what he came up with. And basically, the audience would be sitting there, the doors would be open, and the audience just saw these sort of levers and wheels and so on, and then those doors would be closed, and the thing would be turned around, and they'd be able to have a look from the back. And then a chess player from the audience would be invited to come up and play against this mannequin who was in Turkish dress, and they would play a game of chess. The human would make their move, and then the mannequin would think for a while, and then this mechanical arm would come over and make its move, and it played a very good game, and most of the time the mannequin won. And this became a huge success. It toured all around Europe. Maetzel was a bit embarrassed by its success, so he kind of dismantled it and put it back in his warehouse. But then after he died, his son sold it to a showman called Maetzel, who continued the show. It played against Napoleon Bonaparte and Thomas Jefferson and many other famous people. And eventually, unfortunately, it was destroyed in a fire in Philadelphia in 1854. And of course, we know now that this was a trick, so a human hid in the box. There were rumors at the time that it was like a midget or someone who'd lost their legs in a war or something. In fact, it was a full-sized human. One of the operators was actually 6 foot tall, but still managed to fit into the machine. And if you look at the videos, a few other explanations of how the thing worked. There was this mechanical arm. So obviously this was just a trick, but the important thing is it inspired other people to make things that were useful. So one thing, there was a mechanism where the operator would make a move on his chessboard underneath, and this pulley system made it so that the Turk's arm would follow exactly the same movements as the operator. And Thomas Jefferson was so impressed with this that when he got, later on when he was President of the United States, he constructed a similar device so that every time he wrote a letter, this device would automatically make a copy of that letter, and thus he was able to keep a copy of every handwritten letter that he wrote during his presidency. And more importantly, perhaps, Charles Babbage, when he was 8 years old, he saw the Turk on display at a Royal Exhibition in London, and he was very inspired by this and started to think, well, is it really possible to build a machine that would play chess or do some other kind of computations? And he started to design mechanical calculators. So this was before the age of electronics, obviously, but could you make a device that's purely mechanical for doing counting, for example, for accounting and doing the census and that sort of thing, and the difference engine, and then he designed another machine that was going to be an analytical engine that would do general purpose calculation. Now, unfortunately, he didn't have enough money to build the machines that he wanted. Yeah, he was trying to get money from the government, and the Prime Minister at the time, Robert Peel, wasn't very keen on these things. He asked 3 times for money from the government, and it was always refused. But in 1990, a team of people set out to prove that if he had had the money, he would have been able to build these things with the technology of the time. And this one here is on display in the Victoria and Albert Science Museum in London. Now, Babbage was the hardware guy, but then he teamed up with Ada Lovelace, the daughter of Lord Byron, and she was the software guy. She was the software person, and so she's widely recognized as the first computer programmer. She wrote computer programs to run on this machine that he was designing. And the interesting thing is, even back then, as early as 1843, these people were already thinking ahead about the implications of this kind of technology, including artificial intelligence. You know, the machine is not a thinking being, but simply an automaton which acts according to the laws imposed upon it. So it shows that some people were thinking about these things way back then. And so when the government refused to give them any money, they tried to think about other ways they could raise the money. So one idea they had was that they would build a machine that would play this very simple game of tic-tac-toe, and they would sort of tour that around the country as a means of gaining publicity, and if they could gain money from that, maybe they could use the money to build the more serious computers. They were kind of, I guess, in a way, full of dreams, and this machine never even got built either, actually. But it did arouse interest in the press. And again, this is a contemporary cartoon. This is actually from the 1850s, from the Times of London. This is not a modern-day cartoon. So very forward-thinking ideas. Now, so that's kind of the history. Now, if you remember back to the first or the second week, we were talking about how to classify tasks, and games can kind of be classified along the same way. So remember we talked about chess versus RoboCup. So chess and checkers and Go and Othello, they all fall into this category of games that are fully observable and deterministic. So that's what we're going to start with. Then we move on to things that are fully observable but stochastic. So that's where you have like dice rolls, dice rolls involved. So backgammon, where you roll the dice and that determines what kind of move you can make. And same with Monopoly. And then there's partially observable games like card games, where you can't see what cards your opponent has. So there's information that's hidden from one agent and not the other. And then those games are all discrete, and then later afterwards we'll have a look at how these ideas can perhaps be extended to continuous embodied games like RoboCup Soccer and pool. So the key ideas. So Babbage already understood. Babbage already understood that the computer had to consider all possible lines of play. So this is what kind of makes these. So I should have said what all of these things have in common, of course, is that they're multiplayer, a multi-agent, right? So it's not like solving a puzzle by yourself. You're playing against an opponent, and so you can't really just plan 10 moves. If you're solving Rubik's Cube, you can just plan 10 moves in advance and then do those moves. But here, you don't know what your opponent's going to do, so you have to be able to react to deal with any move that your opponent makes. So that's what makes these things hard. And I think the minimax algorithm, we think was first introduced by Zermelo in 1912 and popularized later by von Neumann. Approximate evaluation was Zeus. Zeus in 1945. He has a Linux distribution named after him. And Norbert Wiener and Shannon. Turing actually kind of published the first chess algorithm in 1951, but he actually was working on it earlier, as early as 1936. And machine learning, well, Samuel worked on checkers. He worked for IBM. He introduced a lot of ideas, but particularly that was where machine learning was first introduced into game playing. And the alpha-beta pruning was introduced by John McCarthy, one of the sort of original guys from the 1956 Dartmouth conference. Okay, so why are games interesting? So as I mentioned, the opponent is unpredictable, so you have to have a strategy, you have to be able to respond to every possible opponent reply. You have time limits. You can't think forever, you can't process all the way to the end of the game, so you can look ahead a certain number of moves, but then at some point you've got to just make an approximate evaluation of how good a position is, how likely you are to win from that position, and there's a trade-off between speed and accuracy. So if you think too hard, your time is limited, so you have to think about how many positions you can evaluate. And so if you evaluate, you have this trade-off where either you evaluate a lot of positions, but using an evaluation which is kind of very approximate and quick, or you have an evaluation which takes more time for each position, but you would then only be able to analyze fewer positions. So, there's this kind of trade-off between speed and accuracy. And because of these things, games have been a key driver in new techniques in both computer science and AI. And a very good example of this is this paper that was written by Arthur Samuel in 1959. And I urge you, if you're interested, to go back and have a look at that paper, because, yeah, he was trying to write a program that would play checkers, and well, I don't know how many of you are familiar with checkers, but it's similar to chess in a way, but quite a bit simpler. Instead, chess has 6 different kinds of pieces, checkers only has 2, and the pieces only move on the red squares, not the white squares, so you only move on 32 squares instead of 64, so checkers has widely been regarded as a sort of child's game that's simpler than chess, but Samuel thought that he'd be able to, even in 1957, he thought that his game was simple enough he'd be able to write a program that would beat the best humans. In fact, his program beat some pretty good humans, but in reality, the computers didn't finally beat the humans until many years later in 1994. So the checkers turned out to be a bit harder than what Samuel's imagined. But the idea was he wanted to do checkers first and get publicity from that, and then he maybe could get more money. It was a similar strategy to Babbage and Lovelace. He thought the publicity from checkers might get him more money, and then he'd be able to work on chess. Anyway, back to his paper. So you can really get the feeling of how innovation was driven by this push. So he needed a way to look things up quickly. So he invented hash tables. Maybe it's an exaggeration to say he invented hash tables, but he introduced new techniques, and that has later become this field of hash tables. He needed to be able to store more data in his computer than the memory that he had, so he invented new types of data compression. And he also invented parameter tuning via machine learning. So you can really see how this has been a driver of these technologies, which are then more widely applicable to other areas. Okay, so let's. One of the simplest games we can think about is this game tic-tac-toe. This is a game you play really with young children. So you have a 3x3 grid, and you can, so the X plays first, and then the O, and then the X, and then the O. And to win the game, you have to get 3 in a row. So the X has to try to get 3 X's in a row, either horizontally or vertically or diagonally. And the same for the O. And then, so if you look at this position here, there's 3 O's in a row. So this is a win for O, so it's considered to be a loss for X. And so from X's point of view, this is evaluated as -1 because it's a loss. Here, X has managed to get 3 X's in a row on this diagonal, so that's a +1 for X. And here it's a draw. Neither player has won, so this is considered a 0. So theoretically, at least, and for this game, you probably could sort of draw out the whole game tree. I think there's about 45,000 possible states or so. And so theoretically, you could draw out the whole game tree, and you could search through all the possibilities and all the way to the end of the game, and you'd have a -1, a +1, or a 0, and then we try, on that basis, we try to decide which is the best move to make. Okay, and so we do this using what's called the minimax algorithm. Now, although this game is simple, we really have to start with something even simpler. So let's consider this situation here. So what's happening is I'm going to so let's someone pretend that they're going to who's going to pretend that they're playing this game with me. Yeah, you don't have to really do anything. So I need a volunteer. You don't have to come up or anything. You're going to play the game with me, okay? Just no, stay there. That's okay. So you're going to choose first, and you have a choice between A1, A2, and A3. And then afterwards, I'm going to choose. And at the end, theoretically, I'm going to have to give you the number of dollars that's shown in the bottom row. It's not real money, it's just a pretend, right? Okay, so the question is, right, so you're called Max and I'm called Min. You're called Max because you want to get as much money as possible. I'm called Min because I want to give you as little money as possible, right? So the question is, which one are you going to choose? Are you going to choose A1, A2, or A3? A1, yep. Good choice. Why do you choose A1? Right. Yes. Very good. So the reasoning goes as follows. You assume that I'm a smart guy and that I'm going to make a clever choice. So if you choose this, because I'm trying to minimize, I'm going to pick the smallest of these, because I'd rather pay you only $3 rather than 8 or 12. So if you choose this, if you assume that I'm smart and you make this choice, you're going to get $3. If you choose this, you're going to get $2. And if you choose this, you're going to get $2. So if you choose this, you're guaranteed to get $3. If you make one of these other choices, you might have to settle for only $2. Yep? Right, good. So this is called the minimax algorithm because at each level, we're searching this tree. So remember, we've done this, we searched this as a kind of depth-first search or an iterative deepening. Well, at this point, it's a depth-first search all the way to the end of the tree. And if it's a min node, we assign, after these have been computed, we pick the minimum of those to be the evaluation here. And then if it's a max node, we choose the maximum. So that's why it's called minimax. And so that's for this very simple tree. And then if you have an actual game, it's somewhat bigger, but you can apply the same principle. So you have these leaf nodes, and then you take either depending on whose turn it is to play, you take either the minimum or the maximum, and you do that throughout the tree until eventually you get an evaluation for the root. Well, you actually get an evaluation for each of these first level nodes, and on that basis you can choose which move to make. And if we want to write code for this, so it's a depth-first search. Now, depth-first search, if you well, you can have a look at the prologue code I gave you for depth-first search, but there's a few different ways to implement depth-first search, but the most felicitous way is with recursive function calls. So and this is a little bit, so with tic-tac-toe we can search all the way to the end of the tree, but we're already putting in here a limit to the depth. So we're actually giving it a depth, and this is actually depth-limited search. We give it a depth, and you're not allowed to search beyond that depth. Okay? So this is how it works. If the node is terminal node, in other words, the game has ended, or well, if it's a terminal node, then we return the actual value of that node, which is usually like 1 for a win and -1 for a loss and 0 for a draw or something like that. If the depth reaches 0, we have to find some other way to evaluate that node. We'll talk about that in a minute, but we have to come up with some heuristic estimate of the value of the node. Now, if the thing has children, we expand the children, we explore the children, and so we want to find, if it's a max node, we want to find the child that gives the biggest evaluation. So we have this value alpha, which starts out at, alpha is the evaluation of the best node so far. So it starts out at -infinity, and then we go through the children one by one. For each child, we recursively compute the value of that child, but reduce the depth by 1. And then if the answer is bigger than our current best value, then we replace it. So this is like, this code here just keeps track of what's the highest value child we found so far, and then when you run out of children, you return the value that you have. If it's a min node, you go the other way, we call it beta instead of alpha. So beta starts out at +infinity, and then for every child, we recursively evaluate that child, and if it's smaller than the one, we're looking for the smallest one, so if it's smaller than our current smallest one, then we replace it. Okay, so this is the minimax algorithm. Is there any questions about this? Now, in practice, notice how this is split between min and max. Now, if we actually sit down and compute things by hand, it's better to follow this version of the algorithm. But if we're actually writing it in a computer, there's a better way of doing this, which is called negamax. And this is how negamax works. And we assume this is called a zero-sum game. We assume that the value for u is the negative of the, if the value for u is +1, the value for the opponent will be -1. If the value for u is +0.7, there'll be -0.7. So the value from the opponent's point of view is always exactly the negative from your point of view. And so we can simplify the code the following way. We're always maximizing, not minimizing, but when we get back the, when we recursively call the algorithm, and when we get the answer back, we put a little negative here, right? So this negamax, is always, so with the previous version, if we're playing X and the other player is O, the evaluation is always from the point of view of X. But here, the evaluation is always from the point of view of the player whose turn it is to move at that point in the tree. So if this comes back with 5, then from the opponent's point of view, it's 5, but from my point of view, it's -5. So it simplifies the code because you put this little negative here, but then you're always maximizing, and instead of sometimes maximizing and sometimes minimizing. And the reason this is better is because this is just the simplest form of the algorithm. In practice, we put a lot more code in here to do machine learning and some other stuff. And if we kept it like this, every time we made a change here, we'd have to make the same change here, and it would just be too hard to keep track of. Here, the code is all kept in one place. We only have to change it in one place. So in computing, we always use this negamax formulation. Okay, so how do we analyze these properties of minimax? we can look at it from the same way we were looking at these other things last week, and the trick here is to remember that it's basically depth first search or depth limited search. So it'll have the properties will be the same. So it is complete so long as the tree is finite. Now that may sound silly, but if you want to search all the way to the end of the game, in tic-tac-toe the game has to end in at most 9 moves, because there's 9 squares, you've got to fill up at least 1 square. You've got to fill up 1 square for each move. In chess, you have to have specific rules to make sure the game doesn't get into an infinite loop. If the same position is repeated 3 times, then it's called a stalemate and it becomes a draw. Is it optimal? It is optimal, assuming the opponent plays optimally. I'll say a little bit more in a minute what happens if the opponent is not playing optimally. The time complexity, so if you're trying to search all the way to the end of the game, the time complexity would be order b to the power m, where m is the number of moves in the game. If it's depth limited, of course, this would be b to the k, if k is where you're cutting it off. But then it wouldn't be complete and optimal anymore. And the space complexity is order bm. So remember, depth first search, the big advantage of depth first search compared to breadth first search is very little space, and we make full advantage of this here. We don't have to store the whole tree, only the branch that we're currently exploring and the siblings. Now, okay, but this time complexity is a serious issue, right? So if we're playing chess, the typical branching factor in chess might be about 25, let's say, or 30. And if we want to search, say, 10 moves ahead, this is a really, really big number, this b to the m. So we want to look for ways to speed up this search. And, okay, well, actually, okay, it's 35. Yeah, if the branching factor might be 35 in chess. And so this is where we get into the idea of alpha beta pruning. Now, I might just take a slight digression here, if I can get this document camera to work, because this issue about the opponent, this issue about an optimal versus non-optimal opponent is quite an interesting one. Let's see. So let's think about this in terms of tic-tac-toe. Now, the picture that I showed you before, well, if you're the X, you've got 9 possible choices for your first move. But if you consider symmetries of the board, in fact, you really only have how many different choices? 3, that's right. You can either go in the center, or in the corner, or on an edge, right? Now, which of these is the best move, do you think? Sorry? The center. Who says the center? Who says the corner? Who says the edge? Okay, well, the centre in some sense is the safest move. You're almost certainly not going to lose if you go in the centre. But who was it who said that the corner is better? Why is the corner better?
Because if your opponent makes a mistake, you can do a sort of insert kind of maneuver.
Very good. If the opponent makes a mistake, you can do a sort of pincer movement. I like that. Okay. Right, so this is, I won't spoil all the fun for you, but let me just do a couple of choices for you. So if you go in the middle, if you go in the corner, taking symmetry into account, how many possible replies does the opponent, what are the places where the opponent could go? How many choices do they have? 5. That's right. Here they only have 2 choices. Here they have 5. They can go next to the X, they can go in the opposite corner, they can go in one of these corners, they can go in the middle, or they can go here. So there's 5 choices. Now let's just consider one of these. Let's say they go here. How would the game then progress? What would be my best, if I'm X, what would be my best move in this situation? You think the centre? Let's try this. All right, we'll try going in the centre. If I go in the centre, O's going to have to go here, then I have to go here, O has to go here. Then what? It's probably going to be a draw, right? Okay. Can someone think of a better option than going in the centre? Down here, yep. Why is that good? Well, the O has to go here to block this. I have to go here, and then, what did you say? Pincer movement, I like that. Sometimes we call this a fork, because if the O goes here, I go there and win. If O goes here, I go here and win. So I'm guaranteed a win from this position. Okay? And this is, I'm leaving this as an exercise for you. These 5 options, it turns out that 4 of them are, for 4 of these choices, I can force a win somehow or other. For the 5th option, O can get a draw, but they have to make exactly the right move, right? So this is, so what's the lesson of this? So if you assume that your opponent is playing optimally, then there's no choice, all these moves are equally good. But if you think that your opponent can make a mistake, then it's much better to go in the corner because you're giving them a much bigger opportunity to make a mistake. And I'll come back to this, when we get to chess, I'll come back to this because it's also, the other thing here is, remember there were 2 options here and 5 options here. That's one of the things that makes this good. The more options, if your opponent is relying on search, the more options they have, the better. Because if the bigger the branching factor, the shallower the depth they can search to. So that's the strategy that humans used against chess programs for many years, is try to open up the board, give the opponent as many choices as possible to maximize the possibility of them making a mistake. All right, let's get back to alpha beta pruning. But we will come back to this. Okay, where are we? Okay, well, before we get to alpha beta pruning, let's look at heuristic evaluation. So if we're playing chess, we have to do a depth-limited search. I cannot possibly search all the way to the end of the tree. So at some point, I'm going to have to just make an estimate of the value of this position. Now, so let's talk a little bit about how to do this. Now, I think most of you should be familiar with chess. One way to evaluate the position is just to count how many pieces each player has. The more pieces you've got, the better in general. And certain types of piece are more valuable than others. So there's like an ancient tradition in chess that if a pawn is worth 1 point, a knight and a bishop are probably worth about 3 points. A rook is worth 5 points and a queen is worth 9 points. Of course, it's not perfect. You know, later, when you get later in the game, bishops are probably worth more important than knights and so on. But this is actually a pretty good estimate. So this is one way to, if you're writing a chess program, let's say you limit the search to depth 6. You do this search and you get 6 moves ahead. If you literally just count the material, how many points each player has, that gives you a pretty good evaluation. Now, if we want to get a little bit more sophisticated, we could add some points for position and interaction. So we could say, well, a knight is normally worth, what's a good example? A pawn is normally worth 1 point, but if the pawn is in this position on the board, I'm going to add a little bit of extra compared to this position. Maybe I add 0.2 because the pawn is here and subtract 0.3 because the pawn is there. I can add and subtract little numbers based on the position of the piece because, if it's in the center, then it's probably more valuable, right? And then I can add a score for interaction between pieces. So this is not a good example, but if you had one piece attacking another, let's suppose, what is it bouncing around? If the knight was over here and attacking the rook, then I could have some extra, add some value for the fact that the knight is attacking the rook, or the fact that a pawn is attacking a bishop. For every pair of pieces, I could add something for the fact that one piece is attacking another or defending another, right? So it doesn't matter where they are on the board, it just matters what's attacking what. So these are actually the kind of features that are used in serious chess programs. Material pieces, some correction for position, something extra for interaction. And just as an aside, so Nightcap, which is one example of such a program, the number of features is, the evaluation is very fast because there's perhaps 2,000 different features, but for any given position, only some of them are active. So I've got 64 different values for the knight being on 64 different squares, but when I look at a particular position, I just say, okay, there's a knight here, so I look in the lookup table, what's the value for the knight being on that square, what's the knight being on that square, and the knight being on that square. So when you do this with lookup tables and so on, the thing is actually very fast. There's 2,000 features, but only maybe a couple of hundred might be active for any given position. Okay, so that's like evaluation. Now, this is bad. So then the question becomes, how can we see the slides. Well, now we get to this alpha-beta pruning. Okay, we're back. Okay. So again, I don't expect you to be experts in chess, but let's just look at this position here, and I'm asking, well, let's suppose I'm thinking about, I'm black and it's my turn to move, and I'm thinking about moving the queen to here. Would that be a good move or a bad move? A bad move, very bad, because the knight could take it, right? And then I'd be in check. So that's a really, really bad move. Now, the important thing to note here is, in order to tell that that's a really bad move, you only had to find one good reply. You know, the fact that the knight can take it, you'd know immediately that's a bad move. But the minimax algorithm would have considered every possible other move. The minimax would consider, you know, moving this pawn up or moving that rook or so on. You know, would consider all those moves. But as humans, when we look at this, once we see this one move that's going to be really bad for us, then we don't have to explore anything else. We know that moving the queen out is bad and we can move on to something else. So the alpha-beta pruning is designed to capture that intuition in the algorithm. And this is how it works. So let's go back to the game tree we were playing before. But this time we assume that these numbers are not actually given to us, that we have to do some effort to compute them. And so we've analysed these positions and decided that the minimum of these is 3. And then you come down here. Well, because of this 2 here, I actually don't need to evaluate those other 2 nodes. Let's think about this a bit more. So max, I don't know what these 2 x's are. All I know is that this is a 2. But this is enough information for me to tell me that max is not going to make this choice. Because if max makes this choice, they can guarantee to get themselves at least $3. But if I make this choice, I might be forced to accept, I can be forced to accept only $2. Maybe it's even worse. Maybe I might be forced to accept even less, but I'm not going to get any more than $2. So I already have enough information to know that this is not going to be chosen. So I don't need to know these 2 nodes. So this is the intuition behind alpha-beta pruning. Okay? Now, I can prune these off and just move over here. Now, when I get over here, because this is 14, I still don't yet know whether this is a good move or not. I might be able to get 14, so I have to keep exploring. It's only when I get to here that I realize, okay, this is a better choice than that one. Now, there's 2 things to note here. One is that this is a very small tree, but you've got to imagine that this is part of a much bigger tree. You know, let's suppose that there's actually, this tree is really of depth 6, but I'm just looking at the top of it. Once I got here, each of these could be a subtree of depth 4. There could be a lot of nodes in these subtrees, so I've pruned off not just little nodes, but entire subtrees. So if this can actually, if it's implemented well, this can save me a lot of time. Okay, that's the first point. And the second point is the order in which you search the nodes is important. So the reason we were able to prune these off is that we searched the best move first. From the point of view of min, this is the best move. And we searched that first, and that enabled us to prune these other ones off. The reason we didn't get any pruning here is because we searched the worst move first and the best move last. Okay, so if we can order the search so that we search the better moves first, that gives us much better pruning. And here's how this is implemented in an algorithm. Now, this is really, everyone has the same reaction when they first see this. They sort of scratch their head and like, how on earth did John McCarthy ever come up with this? But after a while, you kind of get used to it and you see the beauty and the elegance of it. And it's written in a way to make it as close as possible to minimax. But just with slight changes. So the only difference between this and minimax is this thing here, which tests for a cutoff. So we're passing down two values, alpha and beta, and then if it's a max node, we're looking for a max. Well, we're looking for the maximum among the children. But if the maximum ever becomes bigger than beta, then we cut off the search and just we cut off the search and don't search any more children and just return the biggest number we have so far. And the same thing with beta. With a min node, we try to minimize beta, but if it ever becomes less than or equal to alpha, then we cut off the search. And this will become, when we trace through a example in a minute, this should become a bit more clear, okay? And there's also a negamax formation of this. So this is what we use when we program it in a computer. With a negamax formation, we're always maximizing. We're never minimizing. Just the same as with minimax, when we get the recursive answer back, we have to take the negative because it's from our point of view, not the opponent. And the way it works is that when we come back up with negamax, when we do the recursive call, alpha becomes minus beta, and beta becomes minus alpha. Okay. So this gives us the negamax formulation. All right, so let me show you an example. Let me just work through an example here so that you can see how this operates. Yeah. Okay, so we start out. Because if you remember a few key points, you can do this. You can get used to this quite quickly. So we start out with alpha is minus infinity and beta is infinity. When we go down the tree, remember we're not doing negamax. We're doing the straightforward version of the algorithm. So when you go down the tree, alpha gets copied to alpha and beta gets copied to beta. Now, because this is a min node, it's changing beta. So we say, okay, this node is 4. This child node evaluates to 4, so beta gets replaced by 4. And then we go down the tree again, and alpha gets copied to alpha and beta to beta. Now, this is a max node, so it's changing alpha. So alpha becomes 5, and this is where we get a cutoff. Alphas become bigger than beta. So the alpha and beta kind of form a window, and we're only, while we're doing the search, alpha is always less than beta. There's always some gap between alpha and beta, and we're only interested in nodes whose evaluation is between alpha and beta. Right? Now, once alpha becomes bigger than beta, we cut off the search. So we say that we cut this off and we don't need this node. Now, because it's max, the value that's passed up the tree is alpha. So from Min's point of view, it's changing beta, but this 4 is already better than 5, so it keeps the 4. And the 4 gets passed up the tree, and alpha gets changed to 4. Okay, so, and then we continue on the other branches. Now let's just pause for a minute to see why this got cut off. Well, again, Min is making this choice here, so Min's thinking, well, if I make this choice, I'm going to pay $4. No, that's right. If I make this choice, I'm going to pay $4, but if I make this choice, I can be forced to pay at least $5. So I don't need to know this because I've already decided I'm going to choose this. Now we go down the next branch. Again, alpha gets copied to alpha, beta to beta. This is a min node, so beta becomes 6, but there's still a gap between alpha and beta. Beta is still bigger than alpha. Now we copy alpha to alpha and beta to beta. This is a max node, but from Max's point of view, 4 is better than 3 and 4 is better than 2. Okay, so the 4 gets passed back up the tree. From the min node, 4 is better than 6. Now this is an important point here. Alpha and beta are equal, so that's good enough to cause a cutoff. It doesn't have to be, alpha doesn't have to be strictly bigger than beta, it just has to be bigger than or equal to beta. So this causes a cutoff, and this part of the tree gets pruned off. And the 4 goes up, but we already had a 4. Now, just a couple of points here. I'm emphasizing this point because if you search on the web, you'll see different versions of the alpha-beta search algorithm, and many of them, unfortunately, have a mistake where they've just got a greater than sign instead of greater than or equal to. But that's actually wrong. It has to be greater than or equal to, and you can kind of see why people make this mistake. Sorry, let me just go back to the code. Sometimes you'll see a greater than sign here and a less than sign here. People think that it's about two positions having the same evaluation, and they think, oh, it's very unlikely that two positions will have the same evaluation, so I don't have to worry about that, so I'll just put greater than. That's the mistake people make, but in fact, that's wrong, because if you look at this example, where did this 4 actually come from? There isn't any 4 here. There's no 4 anywhere here. This is not two positions having the same evaluation. The 4 started out here, went up here, and then came down here and around here. So what this 4 actually means is, well, I searched here and I couldn't find anything better than the 4, right? So I just make that point. So if you make that mistake and you put greater than, the algorithm will still give you the same answer. You may not notice, but it's going to run a lot long. It's going to take a lot. The running time will be a lot longer than it should be, because it's failing to prune off nodes that should be pruned off. Now we're actually losing information here. The valuation of this node is actually strictly less than 4. It's only 3. There are some other versions of the algorithm that retain an extra variable and keep that information and use that to do machine learning and so on. But this is just the plain version of the algorithm. Okay. And then finally we go down the last branch. Min, beta becomes 3. This gets pruned off. And you can go through and analyze, come up with a story why these things get pruned off. You know, here, Max knows that they can get at least $4, but if they make this choice, they can be forced to accept less than $4. So that's why this gets pruned off, and it's a similar story here. Okay. So any questions about this? Okay, so this is a fantastic algorithm because it's guaranteed to give the same answer as minimax, but it does it a lot faster. And good move ordering improves the effectiveness of the pruning, and you can prove that if you had perfect ordering, the time complexity would be order b to the m over 2, right? So if you did the full minimax, the complexity would be b to the m. Here it's b to the m over 2. Now, that doesn't sound like much, but that's a huge difference. So let's suppose this is like the difference between breadth first search and bidirectional search. Like so if the branching factor is 10 and the depth is 12, yeah, let's say the branching factor is 10 and the depth is 12, with minimax search, the number of nodes would be 10 to the 12, which is a trillion, right? But with alpha beta pruning, it gets reduced to 10 to the 6th, which is a million. So that's an enormous difference between a million and a trillion. And what this means in practice is that you can search twice as deep in the same computation time. So if you could search to depth, if with minimax search you could search to depth 7, then with alpha beta pruning you can search to depth 14. And with chess, if you search to depth 14, even you have a pretty simple evaluation like just adding up the material, you can play a good game. Okay. Any questions about this?
I imagine you lose a lot of that efficiency if you had sort of very suboptimal move ordering.
That's right. If the move ordering is bad, you're going to lose the benefit of this. Yeah. So since you raised that, let's talk a little bit more about chess because this is kind of interesting. So. Yeah, so the question becomes, how do you do the move ordering? How do you ensure that you search the good moves first? Okay, well, first of all, with chess, and yeah, I've done some work on chess as well as other games. So with these, we always use iterative deepening search. So you always search to depth 1, and then to depth 2, and then to depth 3, and then to depth 4, and then to depth 5. And you keep going, and you allocate a certain amount of time for each move, and then normally the way it works is when that time runs out, you just find the best. So you do a search to depth 1 and decide what's the best move on that basis. And then depth 2, and then depth 3. And so when the time runs out, the move you select is whichever search you manage to complete, the move that search told you is the one you pick, okay? And then, so you do the iterative deepening search, and you use the results of the previous search to choose the order for the next search. So we have the top of the tree, you can actually kind of try to remember which moves were best. Well, you have these move ordering heuristics. So one of them says if there was a particular move at depth 3 which caused a cutoff, you remember, for each depth, you remember the move that most recently caused a cutoff at that depth. And so if the idea is if a certain move caused a cutoff in one part of the tree, then very likely that's probably a really good move, and the same move may very well cause a cutoff in some other part of the tree. So you search that move first, and if it causes a cutoff, you're sweet, right? So that's one heuristic. Another heuristic is, or another strategy is called the killer move heuristic. So, that one's called the killer move heuristic. There's another one called the best response heuristic. So you're in some part of the tree, and after this move, it turned out that this was a really good move. So then if you do the same move somewhere else in the tree, then probably this move is a good response to it. So there's these tricks that actually help to make it more likely that you'd search the best move first. Yeah. Well, let me just say a little bit more. So with chess, there's this thing called quiescent search. So let's say you get to a particular node and, let's say you're thinking about material. I've got a queen that's giving me 9 points, but maybe I'm in a position where that queen is about to be captured. So it's actually not very good. So they actually, if you get, let's say you're searching to depth 14, let's say, but if you go 14 moves and then you get to a position where the king is in check or where a major piece is about to be captured, under certain conditions you extend the search to 1 or 2 more moves. So there's more tricks like this, but you get the idea. Okay. So let's talk now about some specific games. So Deep Blue, it's, what is this, 22 years ago now, Garry Kasparov got beaten by Deep Blue in a 6-game match. Some people say that it was should have been closer, or that Kasparov got freaked. This is where we get back to the tic-tac-toe. So you can go back into history. In the 1970s, chess programs played against the Kasparov, played against Korchnoi, and then against Karpov, and then against Kasparov. And the strategy that the humans used to beat the computers was to open up the board. The idea is I want to make the branching factor as big as possible, because if the branching factor is large, the opponent will only be able to search 7 moves ahead. If the branching factor is small, they'd be able to search 10 moves ahead. So I want to make the branching factor as big as possible. And that kind of worked, but then when Kasparov played Deep Blue, you can see, if you look at these games, you can see him trying to do that. He's trying to open up the board and fool the computer by giving it too many options, but then it's just not working. And the computer's making really good moves anyway, and he's getting flustered and stuff. But anyway, and also this relied on hardware that was specifically designed for the purpose by IBM and so on. But of course today there are programs that can easily beat any human that run on a normal PC. Checkers. As I mentioned, Samuel's player managed to beat, the champion of Louisiana or something like this, but not the global champion. And there was this guy called Marion Tinsley who was the human checkers champion for 40 years, from his early 20s to his early 60s. And Jonathan Schaefer's team were able to build a player called Chinook, which could beat Tinsley, one of the things he relied on was an endgame database. So he pre-computed, he looked at all possible positions with 6 or fewer pieces on the board, and he pre-computed for every one of those positions whether it was a win for black or white or a draw. So when you're playing against Chinook, if it's doing a search and it gets to a move with 6 pieces, it doesn't have to do any more computation. It just looks up in a table whether it's a win or a loss. Yeah. And I invited you in the tutorials to think about how those, what would be the way of pre-computing those things. Go. Now Go, the traditional techniques for chess don't work very well for Go because the branching factor is too large. So people tried to, there were these techniques developed in the early 2000s, Monte Carlo tree search, where you do a bit of searching, you search the tree and you kind of build up the tree as you go, and you search a certain number of moves ahead, and then afterwards you just play the game out randomly or according to certain pattern matching, and you keep a record of how many wins and losses occurred from that position, and you have an algorithm that kind of does a trade-off between favouring exploration of good moves but giving some extra emphasis to moves that you haven't explored much before. And a few of us in those days were trying to use convolutional neural networks to learn this, but in those days GPUs were pretty small and we couldn't really beat, we could only beat sort of the players from the 1980s, but you're probably all aware that in 2016 a group from DeepMind was able to use a combination of this Monte Carlo tree search and convolutional networks to beat the human champion. Backgammon. Okay, so those are deterministic games. Then we get to stochastic games. Now, for stochastic games, we need a new kind of node in our search tree, which is called a chance node. Well, in backgammon, you roll the dice, and then the dice determine which moves you can make. So a simpler version of this would be as follows. So again, let's say you're playing this game with me, you're max and I'm min, but the way it works is as follows. First you make a choice, and then afterwards we toss a coin. And depending on whether the coin comes up heads or tails, we go to the left or the right, and then I make a choice which amount I'm going to pay you. So this gives us a generalization of minimax called expectimax. So, okay, if we get to this node, I want to pay you as little as possible. So obviously I'm going to pay you 2 here for 0 and minus 2. But what about this? I don't have neither of us has any control over this. So we just assume that you want to maximize your expected reward. In other words, the average reward that you can expect. So if this is 2 and this is 4, and this is an equal chance, I just say on average this is 3, and on average this is minus 1. And then the 3 is better than the minus 1. Okay, so this is generalization of minimax, but when it's a chance node, instead of minimizing or maximizing, I average. And then this is a little bit subtle, but if I'm doing minimax, the exact values don't really matter. All that matters is whether one thing is bigger than another. But if I'm doing expectimax, I need to have exact values. So the way this works in practice, in chess, as I mentioned, in chess you have these numbers like the queen is worth 9, the rook is worth 5, and so on. So you may get an evaluation of the board that ranges between, say, minus 50 and plus 50. But for expectimax, what I need is a number that tells me the probability of winning the game. So what I usually do is I take that linear sum and then I feed it into this sigmoid function that turns it into a number between 0 and 1, which is a probability. And then, sorry, the other thing, I didn't have a slide for this, but you'll take this up in the tutorials. There's an interesting question, well, is there a version of alpha-beta pruning that applies to situations with chance nodes? And the answer is there is such an algorithm. It's called the AB star algorithm or something, but it doesn't prune off as much. It doesn't prune off as many nodes as alpha beta, but it does prune off some nodes. And in order to apply that algorithm, I need to have an absolute bound, and I need to know an absolute minimum and maximum of what any node can evaluate to. So this is why this number between 0 and 1 is good. If I have an evaluation of every position as a probability of winning, and I know that nothing can ever evaluate to greater than 1 or less than 0, or minus 1 or whatever, if I have absolute bounds, then it allows me to do some pruning. So have a look at the tutorial question and you'll get a better understanding of that. So where were we? That's stochastic games. Then we move on to partially observable games. Now, as I think I mentioned this in an earlier lecture, that the typical way that these card playing programs worked was they would generate 100 possible hands. They would try to guess what's in the opponent's hand. And they would try to come up with 100 possible guesses of what could be in the opponent's hand, which are consistent with the information that they have. And then for each of those 100 hands, they figure out which move they would take, and then whichever one's the most common is the move that you make. That's the typical approach. Now, just recently, the last couple of years, a couple of Michael Bowling's group in Alberta and another group have managed to extend this Monte Carlo tree search to bridge, Texas Hold'em, with a few extra kind of tricks and so on. So that's another approach to this. Infinite Mario. I might say a bit more about this after we've talked about path search. But the current best. Right. So now we're moving on to games that are actually continuous, not discrete. And the best player for Infinite Mario actually uses a variant of A-star search. And these red lines, I'll show you a video later, but these red lines indicate if you chose certain actions, what you predict to be the future path of the agent. Yeah, and on that basis, you make a choice. Then you get games like Pac-Man, which combine planning ahead, path planning, low-level control, reasoning under uncertainty. So the strategy of the ghosts. Each ghost, there's 4 different ghosts and they each have a slightly different strategy, but it includes randomness. You know, when you get to a certain situation, you randomly decide to go this way or that way. And there's a Pac-Man competition where you control Pac-Man, and then there's another Pac-Man competition where you have to control the ghosts. You have to write algorithms to control the ghosts, so that involves multi-agent coordination. And then we get to RoboCup Soccer. So this is, well, let me just say a little bit about this. So I showed you some of these videos. So you've got to do vision processing. So you process an image and you try to locate the ball or the goal if you can. And if you can see the edge of the field or the markings on the field, you try to use that to guess your position. And there's algorithms like the Kalman filter, which, you know, I take what I have an idea of where I think I am on the field, and then I make an observation, and then I update my estimate. So I sort of continually updating my estimate of where I am based on what I observe. And then you also need to look at low-level control, so programming walking behaviors for the robots, turning behaviors, shooting behaviors. And this is a related task, these games like snooker and pool. So this is a pool-playing robot that was developed at Queen's University in Toronto. And, well, it's sort of similar to RoboCup. They have 2 cameras here. They have an overhead camera, and then they have another camera that's looking directly over the cue. And again, yeah, from what you see, you try to determine the position of the balls, especially the white ball and then some other balls. And then you make a plan using a physical simulator. You figure out where you hit the balls, and it's not, I mean, to hit, if you find one ball and you want to hit the white ball to knock that ball and that ball goes in the hole, that's a relatively easy problem. But you also want to control where the white ball goes after the collision so that you can set yourself up for the next shot. And so there, if you hit the ball slightly above the center, it'll put top spin on it. If you hit it below, it'll put back spin. If you hit it to the left and the right, it'll make it spin one way or the other. And so they actually for this, they actually needed vision a little bit beyond what we had in RoboCup. If you look at some of these images, the ball actually becomes a little bit distorted. It becomes a little bit egg-shaped because of the, you know, this, if you take a picture of a big group of people, you know, the people at the edge look like they have really wide faces and stuff because of the spherical distortion in the camera. That has an impact here, and the ball becomes egg-shaped. For RoboCup, we don't really worry about that. We just pretend it's a circle. But for this, they actually do some extra processing to try to remove that distortion because they really need to know very accurately where to hit the ball. Just one more thing I wanted to mention, and then we'll take a break. This is getting back to noughts and crosses. So I mentioned that Samuel... Okay. Okay, so first of all, what I was saying about chess, I said that you might have little numbers that you add for if a piece is on a particular position in the board. How do you come up with those numbers? There's a lot of little numbers that you have to come up with, and it turns out there are ways to use machine learning to try to learn those numbers. And Samuel was the first person to explore this. But Donald Mickey kind of took that up and worked in the same direction, and he came up with this algorithm that's very simple to understand that sort of became a basis for later reinforcement learning algorithms. And he made this noughts and crosses playing engine, which is not an electronic computer, but consists of matchboxes and beads. So he had one matchbox for every possible position, and he had 9 different he had beads in different shapes and colours corresponding to the 9 different moves. And so the way his engine worked was as follows. The machine plays against a human, and every time it's the machine's turn to move, you look in that big pile to find the matchbox that corresponds to the position of the board. You shake it up, and you randomly pull out one of the beads, and that's the move that you do, okay? But then at the end, if you lose the game, then it's assumed you made a mistake somewhere. So you go back to the last move that you made, you find the bead corresponding to that move, and you take it out of the box. So you can never make that same mistake again in that position. If you ever get to that position again, you'll have to make a different move. And so the machine learns by just removing these bad moves one by one. Now, sometimes it'll happen that the last move you made, there's only one bead left in the box. And so you're not allowed to remove the last bead because you always have to have one option. So what you do in that case is you backtrack to the previous move, and you keep going back in the game until you find a place where you made a move and you had an alternate move. Some box where there's more than one bead, and then you throw away the bead for the move you made. Some versions of the algorithm, if you win the game, then you add an extra bead to make it more likely that you'll make that move again. So again, this is very simple, but this became the basis for later reinforcement learning algorithms. And I think in week 8 we'll probably talk about Q-learning and other things that have come along from this. Good. Okay, so I think we'll take a 5-minute break now, and then when we come back, I'll talk a little bit about reactive agents and possibly path planning. Yep.
When it comes to like index engine search,
Yes.
that
Yeah. Thank you. It should be b to the power k.
And is it when it, like, if theoretically, if we were to get a question asking if it was the definition of inclusion, would I say yes, you're going to loop somewhere, or would I say no?
God. I would probably avoid that question if there's any, but I will try to. I will try to amend this. Yeah, I think one of the other thing is just pagination. Yeah, someone. It should be b to the k. That should be yes. Yeah, that's a mistake. It is complete. Well, yes, it is complete so long. Well, It competes as long as the goal, if the goal is within depth K, it will find it. Yeah. Well, so so that's the problem. What do you really mean by complete? Which is why I would try to avoid that question on the exam because it's too ambiguous. But if you manage to pick a depth which is big enough to include the goal, then it will find it.
Also, when it comes to modules, is
Yeah.
everything here an example or is it just the stuff you go through? Because there's Breitenberg vehicles, the other
Ye-
one,
Yes.
there's this part and it says it contains example.
Oh,
But then it
that
says
was
in its
okay.
extension, so I don't like, okay.
Where is that? Oh,
Module, and then it says extension.
okay.
Is it only the stuff you go through?
Okay, I'll try to. It's only the stuff I go through, but this is from last year, I think. Yeah, I tried to sort of
So
keep it up to date, but there's a couple of things maybe I need to refine
not
again.
Breitenberg.
I am going to cover Breitenberg vehicles. I just didn't get to it in week 2 because there wasn't enough time, but I'm going to talk about it right now. Yeah. Yeah.
It seems quite confusing. It's one case. What if the father? Is there any possible case that the father is not entered in the line?
If the father's not entered, then you just
Return false.
return false.
Okay.
So the question is whether you can prove that whether there's enough information there to prove that they have the same name. Yeah.
Yeah.
Yeah. In prologue, false doesn't mean that you're.
It's definitely false.
It doesn't mean it's definitely false. It just means you can't prove that it's true.
Oh, okay. Okay.
Sure.
Okay.
Yeah.
So if for example in some of my questions, it prints out like the answer, but say I have to press like enter or full stop for it to terminate.
Yeah.
Okay.
That's okay. Yeah.
And also like for the testing,
Yeah.
you wrote in that when we're submitting, we should delete all our tests and from the program, right?
Yeah.
Does that mean that if say like I just did instead of like actually writing out tests, I just extensively tested all the like all the edge cases and like all the general cases for my my like assignment? Would that be okay as well instead of like
That should be fine. Yeah.
so we don't have to include like actual tests?
That's right.
Yeah. Okay. Thank you.
Okay, so in the the remaining time, I just wanted to pick up on a couple of topics from previous modules that we didn't have time for at the time, but we'll come back to them now. So first I want to say a little bit more about reactive agents. So remember we had this classification of agents as reactive and model-based and planning and adversarial and learning. So I just want to say a little bit more about reactive agents, and then this will lead into the idea of behavior-based robotics. So talk about Breitenberg vehicles and robots, a bit about reactive agents in nature, and then this behavior-based robotics. So remember, reactive agents choose the next action based only on what they currently perceive, using a policy or a set of rules which are simple to apply. They can't remember, plan, or logically reason, but nevertheless, interesting behaviors sometimes emerge from these simple rules. Now, Alan Turing, at the end of his life, he wrote an interesting essay which was published posthumously, where, among other things, he talks about the importance of embodiment. He talks about the importance, in theory, about building a robot that can travel around and observe and interact in the world. Herb Simon, in his book, The Sciences of the Artificial, he talks about the way complexity sometimes emerges as an interaction between the agent and the environment. So he talks about the idea of if you watch an ant walking along the beach, it's following this complex path, but the ant is actually following quite simple rules, but the reason the path is complex is because the terrain it's walking over is very bumpy. And then we got Valentin and Breitenberg, which I'll talk in more detail about, and he published this book in 1984 called Vehicles, Experiments in Synthetic Psychology, but I think it was based on lecture notes going back to 1969. And then Rod Brooks, in the late 80s and early 90s, wrote a series of essays about this and introduced what we call subsumption architectures or behavior-based robotics. Okay, so Breitenberg, in the late 1960s, Valentino Breitenberg was interested in this idea of how you could design little robots with very simple circuits and observing the way that they behave. So, and he was thinking about this theoretically, but now, of course, later it became possible to easily build these things with Lego Mindstorm kits. So you have a simple vehicle that has two wheels at the back and maybe a little peg at the front so that it can move around and steer a bit. And then you have two light sensors, and then you make connections from the light sensors to the wheels, and then you have a light source. And these connections can be crossed over, or they can be or not, and they can be excitatory or inhibitory. So the simplest example, let's look at this vehicle to start with. So you have these connections are crossed over. So the idea is that if there's no light, the vehicle just sits motionless. But if it detects a light source, it causes the wheels to speed up. And you think about what's going to happen with this vehicle. So if the light source, let's say, is in front of the vehicle but a little bit to the right, both of these sensors will respond to the light, but this one will respond more strongly because it's closer to the light. More light's going to fall on this sensor. So both of these wheels will spin, but this wheel will spin faster than that one. And so the vehicle will turn towards the light. So if the light's on this side, the vehicle will turn towards the right, and if the light's on that side, it'll turn to the left. So it always turns towards the light, and then as it gets closer to the light, will it slow down or will it speed up? Who says it'll slow down? Who says it'll speed up? Yes, it'll speed up because it's getting closer to the light. So these light sensors will respond more strongly because they're closer to the light, so the wheels will spin faster and faster. And eventually it'll just crash into the light. Right? So he called this vehicle hate because it looks as if it hates the light and is attacking the light. Now, of course, it doesn't really, we're anthropomorphizing. It doesn't really have any emotions. It's just like a simple vehicle. But this was his point, I guess, is that by these simple circuits, you can get things that look like they're exhibiting certain emotions. Now, in this case, the wires aren't crossed over. Each one, the left goes to the left and the right goes to the right. So you think about how this is going to behave. Well, when the light is there, it will move forward. But in this case, this is the sensor that's going to respond more strongly. So that wheel will turn faster, so it'll actually turn away from the light. It'll go forward, but it'll turn away from the light. And he called this vehicle fear because it looks as if it's trying to run away from the light and escape from the light, and it'll keep moving until it gets into some dark place, and then it'll stop. Right? So you've got hate and fear. Then he said, well, you can make these things inhibitory instead of excitatory. So here we've got to imagine if there's no light, the wheels will spin with a certain speed, but then when the light is there, the wheels will spin more slowly. So here, this vehicle here, it's running along, the light source is there. This sensor will react more strongly because it's closer to the light. So both the wheels will slow down, but this one will slow down more. And that will cause the vehicle to turn towards the light. But this, unlike the hate vehicle, this vehicle, as it gets closer to the light, it'll slow down rather than speeding up. So if the light is there, it'll kind of, turn around towards the light, and then at some point it'll just stop. It looks like it's kind of worshipping the light. So that's why he called this love. It seeks out the light and just sits in front of it. And the fourth possibility is you have negative values, but they're crossed over. So what will happen here is this sensor responds more strongly, so that wheel will slow down more. So it'll turn away from the light, but the fear vehicle moved quickly when it was near the light. This vehicle moves quickly in the dark when it gets near the light. So it's like an interstellar traveler that travels quickly through interstellar space until it finds a new sun. When it'll slow down, looking to get a good, as if it's trying to get a good look at it, and then it'll move off and speed up again looking for something else. So Breitenberg called this wandering behavior, but because the other three vehicles are named after an emotion, these days we tend to call this curiosity. Yeah. So with these four combinations, we've got hate, fear, love, and curiosity. Yeah. And this is the main point of the book. If you read his book, he then goes on to build bigger vehicles with more sensors and so on, but this is the main point. Okay, any questions about this? Yeah. Now, what about in nature? Well, this is one example of reactive agents in nature, is these like little tiny, often single-celled, even single-celled organisms exhibit this behavior, some multicellular organisms as well. But if we concentrate on the singular-celled organisms, you can look at them underneath a microscope, and in a Petri dish, and even though they've only got one cell, somehow they manage to move towards a food source or sometimes move away from a toxin, and you really sort of scratch your head like, how is this one-celled thing able to do that? And the answer is as follows. These cells, sorry about these kind of hokey graphics, but the cells have these hairs around the edge called flagella, and the cell can turn clockwise or anti-clockwise. So if it turns clockwise, the flagella all kind of neatly bundle up into, like someone's hair sort of thing, and then it becomes streamlined and the cell can move in a linear motion in one direction. If they spin the other way, the hairs all kind of separate out, and instead of moving in a linear motion, the thing just randomly kind of tumbles around, right? So the cells are always switching back and forth between these two motions, and what happens is there's a mechanism there that detects whether the concentration of the food is increasing or decreasing. So if they're traveling in a linear motion and the concentration of the food is increasing, they'll continue to, they'll extend the time for that linear motion. They'll travel a little bit further than they would have. If they detect that the concentration of the food is decreasing, then they'll shorten the time for the linear motion. So they're still switching back and forth between the two motions, but they just adjust how much time they spend in the linear motion. And remarkably, this is enough to make them move towards the food source. They randomly move in some direction, and then they tumble around and randomly move in another direction, but just by moving a little bit further when they're moving towards the food source and shorter when they're moving away, eventually has the effect of bringing them towards the food source. So this is, a very interesting example of reactive agents in nature. And some, as I said, if there's a toxin, they use the same kind of strategy to move away from the toxin. Now, it's not just single-celled organisms that do this. There's some multi-celled organisms like the nematode worm. Neuroscientists are very interested in the nematode worm because the brain has a very fixed and small number of neurons. And some roboticists have actually tried to... So again, it's like the body is sort of thrusting it along, and then it sort of twists the head depending on the concentration of the food. And some roboticists like Barbara Webb have actually tried to build robots that mimic this behavior. Now here's another example. I couldn't find the video of this, but you can kind of imagine these are Lego robots. In the beginning, the pucks are randomly spread around this area, and then gradually they pile up the pucks into neat little piles. So, Rolf Pfeiffer, whose lab this was done in, he's Swiss, and he called these the Swiss robots because there's a stereotype that Swiss people like to keep things neat and tidy. So again, this is a simple example of emergent behavior. What strategy are these robots actually using when they do this? The strategy is as follows. Normally, if you don't detect anything, you just move forward. Now, if you detect an obstacle, so they have three sensors. This is a bit like the Breitenberg vehicles, but slightly more sophisticated. So instead of two sensors, they have three sensors, one straight ahead and one on each side. They're not light sensors, they're bump sensors. So they detect when you bump into something. So if you bump into something on the right, then you turn to the left. If you bump into something on the left, you turn to the right. And if you bump into something directly in front of you, then you move forward. You continue to move forward. So what happens here is the robots they're randomly moving around. If they bump into the wall, they'll turn away and come back into the interior. If they bump into a puck on the left or the right, they'll move away from it. But if they happen to head straight towards a puck, then it'll be the middle bump sensor that detects it, and then they'll keep moving forward. And what will happen is eventually that puck will bump into another puck. So when the puck bumps into the other puck, there'll be a jolt, and the robot will be jolted either to the left or the right. Whichever way, it'll then turn away and move somewhere else, and these two pucks will be next to each other. So over time, you end up with these pucks in neat little piles. Yeah, so it's a sort of simple example, but the robots, they don't have any sort of plan, they don't have any representation of the pucks and the piles. It's just what happens emerging from these simple rules. So then, now I've got to use this as a segue into behavior-based robotics. Now, this was Rodney Brooks, who was like an Australian. Originally, he was from Adelaide, but he worked at MIT for a long time as the head of their AI lab. And in the late 1980s, he wrote a series of essays with titles like Intelligence Without Reason. And he was pushing the idea of these, that we should pay more attention to these reactive agents. And one of his arguments, he was saying that instead of concentrating on high-level games like chess and so on, we should really just look at insects. Can we build an artificial spider or an artificial cockroach? So he built these kind of six-legged robots that were often based on these principles of reactive agents. But then he sort of developed this bit further, and before Brooks, there was robotic systems typically followed this, what's called a horizontal decomposition. So the idea was that you would have a perception module that senses the environment, and then you would have a modeling module that from that perception tries to maintain a map of what objects are in your environment, and then you'd have a planning agent, and then a task execution agent, and then motor control, and the processing would proceed in a linear fashion from one to the other. And this sort of system, there was this robot called Shaky that was built by Terry Winograd at MIT in 1973 that's very, actually, in many ways, very much ahead of its time. And it worked on a kind of blocks world. It would be given instructions like put the blue block on top of the red block, and it would use its camera to figure out where the blue block was and where the red block was. And if the green block was already on the red block, it would have to take it off. It would plan and figure out it had to take the green block off before it put the blue block on. And in some cases, it even had a ramp, and it would push the ramp, and then it would go up the ramp to get the block. And like I said, for 1973, this was very, very forward thinking, but it was very, very, very slow. If you see any videos of this, they're massively speeded up. It might take an hour for it to put the blue block on top of the red block because it moves so slowly. But anyway, Brooks was critiquing this because he said, well, in practice, there was one group of people who were working on the perception and another group working on the motor control. And there was always this fantasy that one day they'd be hooked together, but hardly anyone ever did it. Winograd did do it. That he was an exception, but most people didn't bother. And so he came up with an alternative plan, which is called a vertical decomposition. And so we've got 5 layers here. Sometimes this is called a 3-level architecture because they have 3 levels instead of 5. But this has become a very popular thing in robotics. And the idea is the following, that you have low-level behaviors. You have some low-level behavior, reactive behaviors that connect sensing direct to action. And then you have higher-level behaviors that build maps and so on. And if I can sort of illustrate this with examples. So what's an example of a low-level behavior? Well, avoid hitting things. So you're building a robot that's moving around a home. Let's say the robot is on wheels and it gets to the edge of a staircase. There's that famous scene in RoboCop where the legged robot falls down a staircase. So if the robot can have a little sensor that's on a spring, and when it gets to the edge of the staircase, the spring will go down and it'll detect that there's no floor in front of it, so it goes into reverse. That has to happen really quickly, otherwise you'll fall down the staircase, right? So this is the same sort of thing. A human, if you touch a hot stove, you pull your hand away before the signal even gets to your brain. It may get to the brain stem or possibly even just the shoulder, and instinctively you just pull it away. So you need these low-level behaviors that can take over very, very quickly and are totally reactive. But then when there's no emergency situation, then you may want to do something more sophisticated, so you may want to build a map of your environment. So Rod Brooks, he did a lot of work on these automatic vacuum cleaners, which eventually, the Roomba, the first commercial, he designed the first commercial automated vacuum cleaner, which went on sale in 2006. So you can have these sort of mid-level behaviors that build maps, and then you're going to have higher level behaviors that do planning. And so this is sometimes called a subsumption architecture, because you've got these behaviors that are all running simultaneously, and it's possible that a higher level, well, there was a lot of debate about this. Should it be the low-level controllers taking control from the higher level? Should it be the other way around? And the answer is it depends on the situation. So in those emergency situations that I described, the low-level behavior has to have the ability to just stop whatever the robot was doing and react immediately to the emergency. But there are other situations where the robot may be doing some low-level behavior, and then it gets stuck because the floor is slippery, and so the robot's trying to move forward but actually isn't going anywhere. Then some higher level behavior has to detect the lack of progress and say and take control and end that low level process and do something else. So sometimes the low level is taking control away from the high level, sometimes the other way around. But it's called this subsumption architecture because you've got these different behaviors and they can control this sort of switching between them. Okay, so that's just a very brief introduction to reactive agents. Are there any questions about this? Yeah. All right, where are we? There's one more topic I wanted to cover, which will be the last thing for today, which is about motion planning. So, someone was asking, last week someone was asking what's the practical application of A-star search? Is it just for things like Rubik's Cube, or can it be used for other things? So I wanted to talk about this motion planning because it's a good example of taking an algorithm like A-star search and kind of enhancing it and adding it and adapting it to a more real-life situation, which is motion planning. But before we get to the A-star approach, I just want to say a little bit more generally about motion planning and other approaches that have been used. So the idea here is you've got a robot and it's moving around. It could be moving in an office environment. It could be moving on the RoboCup field. And you want to plan a path for the robot to get from one place to another. Now, one approach to this that dates back to the 1970s is called an occupancy grid. And so the robot, first of all, let's have a look at the sensors that are on this robot. So that thing there is not a sensor, that's just a gripper to pick things up. But you see that there's there's 5 sonar sensors here, and this thing here is called a laser rangefinder. So it's like a laser that scans across 180 different directions and repeatedly scans and tries to look for an obstacle in that direction. And both of these do a similar job, and if you look at a more modern robot, instead of the laser rangefinder, it might have what's called a Swiss Ranger. But what these things do is they try to detect, in each direction, they try to detect what's the distance to the closest object in that direction. And the sensors are a bit noisy. You can't rely 100% on what they're telling you. Sometimes they see phantom objects. You have to have methods for filtering out the noise and so on. But this is an example of what you might see. So there's an obstacle here, and there's an obstacle here. So when the thing does this range finding, it detects that in these regions there's empty space, but there's an obstacle. If it goes in that direction, it'll hit an obstacle, and the same thing here, right? And you also notice that this Cartesian grid is, in this case, is in global coordinates. So in order to maintain this map, the robot may have to keep track of which direction it's facing and where it is so that it can convert between local and global coordinates. But anyway, it has this sort of Cartesian grid, and it tries to remember which of these squares have an obstacle and which ones don't. So the idea is if it's trying to find a path over here, it would have to go through this valley rather than bumping into that obstacle. Okay. So how does it plan the path? Well, one way is called a potential field. So the idea here is you imagine that there's an attractive, if the place you want to get to is over here, you imagine there's an attractive force pulling you towards the destination, but then you imagine there's a repulsive force pushing you away from these obstacles. And if you sort of physically combine these vectors, these forces, if you're lucky, that may end up guiding you in a path that goes between these obstacles and gets you to destination. So that's a sort of simple approach that sometimes works, but it can get stuck in the same way that we were discussing before, that let's say you happen to wander into here, there's an attractive force pulling you towards the goal, but there's a repulsive force pushing you away from these walls. You could end up with you could end up in a situation where they balance each other out, and you're stuck, and you just don't move anywhere. So then we get to a slightly more sophisticated model, which is called a vector field histogram. So we have a Cartesian grid, as like we showed before, that's in rectangular coordinates, but we also maintain another version which is in polar coordinates. So polar coordinates means relative to the position of the robot, you measure the angle and the distance to the objects, and you're continuously updating both of these maps. So you've got it's like a global Cartesian map and a local map in the polar coordinates, and based on this information you try to identify candidate valleys. So a candidate valley is a contiguous sector which have low obstacle density. So back here, this here would be a candidate valley, and perhaps this and this would also be candidate valleys. So the idea here is you're doing a little bit of search, you're identifying 3 candidate valleys, and then you're trying to decide which one of them would be the best one to take. And it's a trade-off between how wide the valley is. You prefer wide valleys over narrow ones, but you also prefer valleys that are taking you in the direction of the goal over others. All right, so I won't go into any more details. I'm just telling this as like an alternative method. But the method I want to concentrate on is how to do A-star search in this situation. So we have to start out. Now remember, A-star search is on a graph normally. So if I give you the map of Romania, that's a graph already. If I give you Rubik's Cube, you can turn it into a graph or pretend that it is a graph. But here I'm just giving you a continuous situation. How can you build a graph? How can you build a graph from that continuous situation? So this is the start and that's the goal. So the particular application we were looking at here is RoboCup. So the obstacles are the other robots, and I want to get here. So the idea is, how can I plan a path? How can I plan a path from the start to the goal? So I want to have a graph to search on. Now, what I've shown here is actually the dual of the graph. So the real graph that I want, what I want to do is actually I want to be moving through. Okay, so I've triangulated. The first thing I do is I triangulate the space, and I chop the thing up into triangles, and then the path that I'm going to plan goes through the centers of different triangles. So maybe I'll go from here to here to here to here, and so on, and this will get me a path to the goal. Sorry to jump ahead, but this is actually what the real path might look like. Is the thing shown in purple. So the green thing is the dual graph. So I have to start with the green triangulation first, and then the dual of this is actually the graph that I'm searching on. So there's a little bit of terminology here. So the green thing is called a Delaunay triangulation. And it's applicable situations where the environment is well mapped by overhead cameras, and you've got obstacles. So as well as RoboCup, this could be used in museums or shopping centres or that sort of thing, old people's homes. And how do you... I could give a 5-year-old a crayon and ask them to divide this up into triangles, but how do you actually do this automatically? Well, you consider all... So the vertex... What are the possible vertices of this triangulation? Well, every obstacle is a potential vertex, and then I specify certain vertices around the edge, so maybe not just the corners, but these are predetermined as possible vertices. So I've got a set of possible vertices, but I can't include every edge between every pair of vertices. So this edge is not included, for example. But in general, I'd want to have shorter edges rather than longer ones. You know, there are various ways to triangulate this. So look at this example. I've split this up as the triangle here and a triangle here. I could have split this up. I could have included this edge and not that one if I wanted to. So there's lots of different possible triangulations, but I want one that's likely to give me a good path. Okay, so this is what happens. If there's n edges, then there's n squared over 2 possible... if there's n vertices, then there's n squared over 2 possible edges. So I consider every possible edge between one vertex and another, but I just add them one by one according to the length. I add the shorter vertices first. And I don't add any segment that crosses an existing segment. So here, this one is quite short, so I add that, and then this one is short, and this one is short. But when I get, for example, when I get to this edge from here to here, I don't add it because it would cross this edge that's already there. So I go through the whole list of edges from shortest to longest, and in each case, I add the edge to the diagram only if it doesn't cross an existing edge. And there's there's routines in OpenCV there's graphics routines to tell whether one edge is going to cross another. So that gives me this Delaunay triangulation. Whoops. And you notice some edges are marked in red. That means this edge is too short. I can't pass between those two obstacles. They're too close together. Okay, so this green thing is called the Delaunay triangulation. Now, as I mentioned, the actual graph we're searching on is the dual of this. So the vertices, and it's called the Voronoi diagram. So the Voronoi diagram, its vertices are the centers of these triangles, and the edges are edges that go between neighboring triangles. So you have to try to imagine that's the graph that we're actually going to search on, the Voronoi diagram. Yeah, we prune arcs that are too short for the robot to traverse, those little red ones. And now we can use A* search on the resulting graph to find a trajectory for the robot. Now, but you see, if we were to do this, you might get a path that's quite long compared to... It would probably find a path that goes like this, from here to here to here to here. and then around here to the goal. So we can use A star search to find this, but you see there's two issues here. Firstly, the distance may be longer. Because I'm always going through the centers of these triangles, the distance may be longer than necessary. So the actual path would be going all the way out here, when in reality I can maybe cut that corner and go a little bit earlier. So we want to look for a way to kind of shorten that path. We know that this is going to go, that it's going to cross this edge. We know which edges the path is going to cross, but maybe we want to find a path that's shorter that still crosses those edges. That's one issue. The second issue is that if the robot is making turns that are too sharp, it may actually take longer even though the path is shorter. So if you think about these two situations, it may be that the shortest distance path is this one. It may be that this path is, in terms of distance, longer than that, but the robot might be able to traverse this path faster than that path. Because it's doing these tight turns, it would have to slow down. And whereas here, because this is a smoother path, the robot may be able to travel faster along that path. So maybe we want to actually minimize the travel time rather than the distance. Okay, so this is the system that we developed for this optimal trajectory planning, right? First we do the Delaunay triangulation. We do A star search using paths composed of, we do A star search, but instead of, so instead of doing like a path, A star search, if we apply it directly, it's going to give us a piecewise linear path, but that's not quite what we want for the robot, because the robot can't literally go in this direction and then suddenly change to that direction. We really want a smooth path. So what we do is we create a path that consists of curved line segments joining neighboring edges. So we say, okay, this is the series of edges I want to go through. I want a curved path from here to here, from here to here, from here to here, and by putting all these little curved paths in, I create a smooth path, and these curved paths are created by what's called cubic splines. So I have my time variable t, and then the x and y coordinate are expressed as cubic functions of time. Whoops. So what does this mean? So x at time t is written as a times t squared, a times t cubed plus b times t squared plus c times t plus d for each of those little segments, and y is written in the same form. So if I write the thing in vector notation, I can write it like this. There's this vector times t cubed plus this times t squared plus this times t plus this. Now, we didn't invent cubic splines. Cubic splines have been used for a long time for graphics, but what we introduced was we modulated it by time. So traditionally with cubic splines, they just, for a given segment, t goes from 0 to 1, but we wanted t to go from 0 to s, where s is the actual amount of time that's taken to traverse that segment. And the sum of s for all of those segments is the thing we want to minimize, because that's the time taken to traverse the whole path. And then we have certain physical constraints on the robot. Now, I didn't make a I didn't make a graphic for this, but I'm just going to show you, I'm just going to draw a little picture of this. So the kind of robot that we use is is called an omnidirectional robot. So first we determine for the robot what is the max velocity of the robot. Let's call that v. So you just try to drive the robot as fast as possible, measure its speed, and that's called v. And then you try to determine the max acceleration, and we call that a. Again, experimentally you can determine this. And then what happens is when the robot's traversing a path at any given point in time, it has a certain velocity, which is a vector, and it has a certain acceleration, which is also a vector. Sorry, its real velocity is p prime of t, its position is p of t, its velocity is the derivative of that with respect to t, and its acceleration is the second derivative. And so we can draw a picture of p double prime t over a plus p prime of t over v. And the square of this, we assume, is less than or equal to 1. Okay, now where does this equation come from? Well, remember these are vectors, so here's a diagram. So this direction here is measuring p prime t over v. This vector here is p prime t over v. And remember, v is the maximum velocity, so this vector is, the robot could be traveling in any direction, but its maximum velocity is v, so this velocity divided by maximum velocity has to be a vector that's of size at most 1. So the length of this vector can't be bigger than 1 because v is the maximum velocity. But it can be anything smaller than 1. So we can plot the current velocity of the robot in this circle, and then the acceleration is some other vector, and I divide it by the maximum acceleration. And what I'm saying here is that when you add these two vectors together, it has to still lie within this circle. And this makes sense because it's saying, well, if you're traveling almost at your maximum possible velocity in this direction, you can't really speed up much more, right? But you can slow down a lot. So I'm allowed to apply this acceleration because it's slowing me down, but it's very hard for me to speed up, right? And then if I apply this acceleration, well, it means that I'm turning in a certain direction. So this provides a mathematically simple constraint on the kinematics of the robot that actually matches the reality pretty closely. Okay, so this is what we used for our system. So I apologize there's so much detail here, but I really think it's good for you to see how a complete working system can be built on these kind of principles, okay? So what happens here? So this is an example of possible paths. And remember, each of these paths is broken down into segments between these edges. And in here, there's a cubic function, and in here, there's a cubic function. And the velocity, the final velocity of this segment has to be the same as the initial velocity of the next segment. And this kinematic constraint has to be satisfied all the way along the path. And I want to find the minimum time path that satisfies those constraints. So how do we do this? Well, the first thing is this equation here turns into a cubic equation. Now, I can't afford to test this. This constraint should apply all the way along this trajectory, but I can't afford to test it all the way along, so I just test it at the endpoints. I test whether the acceleration here is not too big and whether here is not too big, and I just assume that if the constraint holds at the endpoints, it'll hold in the middle as well. That's not guaranteed, but in most cases that is going to be true. So this, makes the thing computationally feasible. And so this becomes a constrained optimization problem, and I start with a path, and then I just gradually adjust these crossing points to try to reduce the time taken for each segment, right? So, I might start with this segment here, taking this path to the goal, but then I gradually move down to here to get a faster trajectory to the goal. And I do that for each segment, and then for each sort of topological path, I try to find the minimum length trajectory for that topology, and then I'm choosing between different topologies. So I could either go around this way, or around this way, or around this way. I've got multiple paths to choose from. And I use A-star search we use A-star search to do this search, and then the only remaining question is, what is the heuristic? And basically, so if you're at let's say you're at this point here, well, I just assume I know what the distance is from here to the goal, so I assume that I can travel that distance at my maximum possible velocity. So that'll definitely give me an underestimate of the time to get from here to the goal. So, so this system, it takes A-star search and then adapts it to a continuous system. You throw in some cubic splines and some local optimization, and it gives you these optimal trajectories. And we did actually use this in the RoboCup competition. And if you're interested, you can go and have a look at the details in this paper. Okay, so these details are not kind of examinable, but I just thought it'd be interesting to see this as a real system. Are there any questions about this? Yes. Sorry, say it again. Slide 17. From these slides? Oh, yeah. Oh, yes, here. Yep. Yes. Good question. I think it's a straight line to the goal. I think it's a straight line to the goal at the maximum velocity. Yeah. Yes. Okay, so right. So these A, B, C, and D are the parameters for that segment of the cubic spline. So you've got 8 parameters here. Now, so how many equations and how many unknowns? So the beginning and end point have to lie on these 2 lines. So if I put t equal to 0 here, if I put t equal to 0, this initial point has to lie on that line segment. So that gives me one constraint. And then the final point also has to lie on the line segment, so that gives me a second constraint. And then I've got 2 cubic equations. The velocity at the beginning has to match up with the final velocity from the previous segment, and also at the end. So that gives me 2 more equations. So I've got 4 equations. And then usually this, and then I've got this constraint. And I've got the constraint at the beginning and the end. And it's a constraint on, So basically, it's a constraint optimization problem, or it's a constraint optimization problem. You're trying to find those, you're trying to find those 8 numbers subject to these 4 equations, plus this constraint at the beginning and the end. Yes. The triangulation. You just consider, okay, let's suppose there's 20 vertices in the graph. Let's suppose there's 20 vertices specified, which is all the obstacles and the thing. So if there's, or let's say there's 21, so then I've got the number of possible edges is 21 times 20 divided by 2, so that's 210. So I have a list of 210 edges, potential edges. I sort them in order of length. And then I go through the list and I decide for each edge whether to add it or not add it. So I add it so long as it doesn't cross an edge that's already there. And eventually, if I go through all the edges and do that, it'll lead to this triangulation. It's possible you could add the longest one, but it's probably unlikely. Yeah. You're more likely to add shorter ones. Yeah, there's no guarantee that you won't add a long one. I have to say I'm a bit confused here whether this, I kind of feel this edge should have been added instead of that one. So there's something a bit suspicious about this picture, but yeah, you get the general idea, yeah. Maybe you're not allowed edges, I'm not sure. Maybe these edges are not allowed for some reason. Well, they should be allowed though. Yeah, but if the goal was really in the corner, maybe it might. Yeah. Sorry, what was that? Yeah, it looks, maybe it's constrained that every triangle has to include an obstacle. Yeah. Where are we? Okay, I just wanted to show you one final thing before we go, which is I want to look for this Super Mario. This application to Infinite Mario. Because again, this is the same kind of idea. So this was a competition. That's not the one, must be this one. This was a competition that started in 2009. It was originally, the idea was to promote machine learning, but in the end, the winning entry didn't actually use any machine learning. So what they did was, well, first of all, they reverse engineered the physics. So this is, we talk about known environments versus unknown environments. You're not kind of told in advance what the physics is for Mario. It's not normal physics. It's like you can fall into a hole, and if you do the right sequence of actions, you can actually jump out of the hole. That's not normal. So the first thing these guys did is they put a lot of effort into trying to figure out what are the actually underlying physics in this game. If you do a certain action, if you're in a situation you do a certain action, what's going to happen, right? That's actually not trivial. And once you know that information, then it's much easier to create an AI to play the game. If the AI didn't know the world model and had to learn it, it would be much harder. Okay, so it's important to understand that. So, but these guys managed to reverse engineer the physics, and then what they do is they use basically an A-star search, kind of similar to the robot navigation. So these red lines are actually indicating. Whoops. I accidentally disliked the video. So these red lines indicate, so you're trying to choose it. So the graph in this case is like which actions you're going to choose, and then you have to discretize the time. You say, okay, I'm going to choose an action at this point in time, and then some short time later and some short time later, and then these red lines indicate what trajectory you expect to follow if you do that sequence of actions. And then I don't know exactly what they use for the heuristic function, but you can imagine, they use some heuristic function and some A-star search, and this is how they're able to play the game. So again, this is not, I don't know if this is, you see how he went into the hole and came out again. I don't know if you would call this quite a real-world example, but it just shows you some extension of this to a more sophisticated domain. Any questions about this? Or anything else? Any questions about games? You could still create AIs for different Mario and test them out. Is that right? Cool. can still do it. Okay, what's the time? 12:46. Okay, that's been a lot of material for today. I think we'll take a 10-minute early mark. Yeah. And I'll see you next week. Oh, did you? Oh, okay. Oh, somehow I missed it. Yeah, please send it again. Did you send it to Blair at csc.unsw.edu.au? Okay, send it again and I'll try to. Yeah, that should be fine. Yeah.
Wait, sir.
Yeah.
Just one question. In assignment, the question where it says square root of negative numbers. Like I know negative numbers don't have an output, so we should just remove the negative numbers from the result.
Oh, the negative number. You can just, you won't be tested on that.
Like if you have result,
Yeah.
so then let's have a list
Yeah.
of 0, minus 2, and 4.
Yeah.
Should it just result 0 and 0, or should you?
It's a good question. I wonder what Prolog does.
What I did is I made an option to remove the negative numbers and
Yeah.
just do 4. See, like if you have a list 0, minus 2, and 4, I've given an output like this.
That does make sense. Yeah. That, I mean, you won't be tested on that, but actually, that's a good solution.
And just one thing, like for the family solution, like regarding this, like for the same name, like I've incorporated some solutions from the Prolog dictionary on the relationship between grandparents and siblings.
Right.
Like I've modified it, included some of my own code. But when I reference it, like I should reference it broad code and the dictionary.
Yeah. That's
Like on top of the code, I'll just mention broad code and I'll mention for the same name.
That's a good idea. Yeah.
Flexible about
Because for the same name, like you have uploaded the solutions for.
For the that's right.
Yeah, for the
exercises.
Yeah, for the exercises. So I've taken some of those solutions and I've cited it.
That's good.
Yeah, that's what. I put it as comments on top of the predicate.
Great.
So at least you will know that I've taken it from there.
Exactly.
Yeah, these are my main doubts. Yeah, this is what I've done for negative numbers. If I have a negative number, do this.
That's
it's 0, minus 2, 4. Do 0, 0.
That's
4.
like an elegant. That is an elegant solution. Yeah. That's good.
That's what I've done.
When you're talking about this B course here,
Oh yes.
actually I didn't understand it very much. This algorithm.
Oh yeah.
Like, why does this have to go here? Because why does this have to carry on to? Oh, because that is the maximum available.
Yeah. See, max always uses alpha and min always uses beta. So min.
So when we have 4 here, that means A will be 4.
That's
right.
right.
I mean alpha will be 4. Is it like that, or beta become like that's?
Yeah. When it comes to here, it becomes beta. The 4 gets passed up the tree. But because this is min, it's changing beta. So beta becomes 4. And then beta gets passed up the tree, and this becomes alpha. So it depends if it's max or min, whether it's changing alpha or beta. Yeah, I just have a look. I mean, if you look in the video, I got a video where I work through another example.
Okay, I'll check
Just
that.
try to, and there's a tutorial question, so just try to work through a couple of examples yourself and
Sure.
see if you can.
Sure. And the Prolog labs, like, do they teach anything like the tutorials there, or we have to just go ask them for any doubts? Like,
You just ask them. when you have questions.
I didn't know about the labs at all. I was just attending the tutorials.
Right.
So I was thinking, why are they not doing any program labs?
Oh, yeah,
Labs?
sorry, I probably should have. I'll put up a notice just to remind
Oh,
people.
that's
So, yeah, there's still a week before the
Yeah,
assignment.
sure. Okay, thank you.
Problems about the missionaries and cannibals.
Oh, missionaries and cannibals, yeah.
So we used to do the depth search, and the last tutorial they told us to change it breath versus search. So the problem is I don't know because based on what we learned before, those two kinds of search is based on the length of each path of each node.
Right.
Yeah, but for these missionaries and cannibals, but their length is equal. I don't know. So what we really want to do it's like we only need to find the last soul path all the way obviously, but I don't know how this works. It's like
Have a think about it. Yeah. Well, did you have a quick question? Or?
No, I don't have many questions. I just want to see that.
Oh, the alpha beta thing? Or, yeah.
Yes, can I take a picture of it?
Yeah, sure.
Thank you. You go on.
So you're saying that you're wondering whether the cost function is correct, or you're wondering whether the depth first search and breadth first search is the right one to work?
exactly. It's like I don't know what we really want by using it to. We both want to find a path of the game, but
The idea is to just get to the goal.
yeah, just to get a goal, but I think there's no difference between depth first and breadth first search.
For this small example, it probably doesn't really make a difference which one you use. They'll both be roughly equal.
Yeah, so it's like when we're using depth first search,
Yeah.
we just go down.
Yeah.
There for breadth, there are many, and we go down there, and we get the other nodes. But what is the rule to make I don't know.
You mean with depth first search, which you have several children, which one do you choose?